during the previous session, we talked about the typical approach. With that, we make a strong assumption about the hemodynamic response. So we use some standard curve to model the hemodynamic response embedded in the signal. So now we switch to a different, dramatically different approach. So we don't make such a strong assumption about the hemodynamic response shape. Instead, we're going to use the data to capture the hemodynamic response shape. So the way we do it is using a so-called tent basis functions. So multiple basis functions. So each basis function is a tent shape, like the camping shape. Mathematically, it's defined as this expression. The way we do it is basically at each time point. Suppose we want to, for example, let's switch to the next slide. Suppose we want to cover 12 seconds of hemodynamic response. So like this. So each time interval is 2 seconds. So 6, we cover 12 seconds. So with those 12 seconds, that period of time, this case, we use 5 tenths. So each of them we put each of them at some specific time location. So each tent has a unit height. So it's like a ruler, or put it at those time post locations. So with those unit rulers, then we depends on the data point at those time locations. So we estimate the hemodynamic response. So in the end, at each location, we get the beta values. So in the end, those 5 betas plus the beginning and the end, which hold at 0. So then we get the overall hemodynamic response. In addition to that, we also have the hemodynamic response magnitude, which in this case is we can pretty much approximate with the maximum value among those 5 betas. So that's the basic idea. It's pretty straightforward and intuitive. But the major challenge is that instead of 1 beta per condition or per task, in this case we have 5 betas. So we have to deal with at the group level and also even at the individual level. How do we summarize those betas to have some statistical significance to show the evidence of the hemodynamic response? So that's the idea of multiple basis functions. So with that, basically, each voxel has will have those multiple beta values in the end. Another subtlety is that in affinity, usually this approach does, just like the typical modeling approach with one standard curve, it does not require that the stimulus timing has to be locked with the TR grids, unlike the other implementations available in software packages. So here is an example that demonstrates the modeling approach. So in this case, we have 10 rounds. Each round has 136 TRs. Each TR is 2 points. So that's a data set that was, I believe, was published more than 10 years ago in that paper. So this is an experiment that has 4 conditions. It's a 2x2 design. There are 2 factors. The first factor is the image, the video type. It's either it's a human video or it's about some tool movement. So that's one way to categorize it. Another way to categorize each video is that either it's a real image or it's a dotted video image. So with the 4 different conditions, so basically it's a 2x2 or so the 4 combinations. So that's basically the layout of the experiment. So I think that's it. There are 4 conditions. Those 4 conditions can be characterized in 2 different ways. One is the object type. So it's the image. That image can be a human or can be a tool. Human is just a picture of a human or some description of human. I will show you a real image or a video of those 4 conditions later on. A tool can be a hammer or can be a saw or just human tools. that's one different way. So it's either human or it's just non-human object. Another way is the video can be for both human and tools, can be a real image versus is a descriptive image, like different dots to show that's a human or it's a tool. So that's a 2x2 design, right? So 2x2 is 4 different combinations. So that's basically, we have 4 tasks. I mean, this then the subject in the scanner will visualize those 4 images. Then each probably repeat many times. So this is basically, this shows a human image, right? So this is also a human image, but it's dots. So this is the tool, the sword. This is the hammer, right? So this is the 4 different types of images. So on the left column, it's a human. On the right column is a tool. So that's one way to categorize those 4 tasks. Another way is that horizontally, this is a real image versus the second row, that's the dotted image, dotted images. So that's pretty straightforward. So here's basically shows, see. So this is the human moving, this is the hammer, right? So those are the 4 conditions. Now, if we look at the design matrix, it's pretty messy. That's because we have 10 rungs, right? So there's each rung we model with 3 parameters: the baseline, linear drift, plus the quadratic. So this is the second order of polynomials. So each rung will have 3. So 10 rungs, we end up with 30 columns for the baselines and the slow drift. So then we have 4 big columns. Each big column is 4. Remember, we have 4 conditions. Each big column contains, in this case, we have 7 tenths. So we have 7 regressors for each task. 4 tasks, that's 7 times 4, 28 regressors. So the traditional approach, we would only have 4 regressors for the task. But here, even each task will have 7 regressors. Those 7 betas will characterize the hemodynamic response. So this model is more complicated. You can need more data, of course. So the last 6 columns, of course, those are the head motion parameters, right? I mean, we could plot out this, but the plotting is very crowded, and also because this is the tent, there's not much to say about the tent. Unlike the traditional approach, you say the curve, right? So this, you just say those are dots shifted. So that's why it's if we use the plot out, probably, the plot out for the head motion parameter is probably still a good idea. But since we have here we have, I don't know, 50 regressors totally, or maybe more than that actually. 30 plus 28, 58 plus 6. So that's a 64. So in the end, actually, this data set is not a good idea to demonstrate because it doesn't show us much about the subtleties about the hemodynamic response curve difference. Wednesday I'm going to show you a beta data set which really shows the subtleties. Here it pretty much looks like in the end it's about the magnitude. We don't say much about the even the magnitude is roughly at the same location, and we don't say much differences in terms of the undershoot and in terms of the upstrokes. So this is not actually a good data set to demonstrate the modeling approach. All right, so that's sometimes people call this approach is called deconvolution. That's because convolution versus deconvolution is basically it's like multiplication versus division. So in this case, we don't make an assumption about the hemodynamic response. So we have to find out the hemodynamic response. So that's why it's sort of like we only have this, like a multiplication, we only know 1, which is stimulus timing, but we don't know the hemodynamic response. So that's why we have the data. So we have the final product. We know one of the multiplier, but we don't know the other. So that's why called deconvolution. It's like a division, right? So the word convolution it's like you roll the carpet, right? So you roll together. That's called a convolution. Deconvolution, basically you go the other direction, right? So that's the concept of deconvolution. It's like deviation, you have the final, in our case, the final product, which is the EPI data set. So you try to find out the hemo response curve, the function. Of course, this approach is not always, perfect. It has pluses and minuses too. The good thing is you give up. Usually, most of the time, the detection power is much higher. I'm going to show you at the group level because that's even more dramatic. Show the subtleties about the hemodynamic response capability. But the downside is that's why it's not popular is because you have to know how to do it, and also the challenge is how to check the final result. You're not dealing with just one beta. The multiple betas, how do you describe the result? How to summarize it? So that's the challenging part. And also, if you don't design your experiment carefully, you may end up with something cannot solve the equation, because with so many regressors, you may end up with multicollinearity problem. So some regressors that overlap with each other, then not differentiable between different conditions. So that's another challenge. So that's why when you design experiment, you probably better try to avoid that situation. Through different ways to arrange the sequence. One normalization, and also be careful separate the tasks to some extent. So that's the two extremes. Either you do make a strong assumption, which is a traditional approach, or you don't make an assumption at all about the response shape. There's a middle ground. That middle ground is the SPM approach. They have the concept of three curves. First one is called a canonical curve, which is this blue curve. This orange curve is they call it canonical hemodynamic response. Then there's the second one, which is the blue one. They call it temporal derivative, which is basically the first order of a time derivative. That's the third one is they call it dispersion curve. So the second one, that's basically give you a wiggle room, even though the orange one shows the peak occurs there, but the blue one will try to shift the peak, where the peak occurs, shift that the location of the peak a little bit. So that's the flexibility of this temporal derivative, where the peak location give you that a little bit wiggle room. The third one is basically make some adjustment about the width of this peak, the peak. For example, when I talk about the half maximum, the width of here, the green one will try to squeeze it or maybe extend a little bit. So that's this approach basically you modulate a little bit about the peak location and the width of the peak. It doesn't do anything. Doesn't do much about the undershoot. Also, in the end, nobody cares about the shape difference. So that's why even though you end up with 3 beta values, usually people just throw away the second and the third beta values, then focus on the first beta. So this modern approach, they do give you a little bit adaptability for the shape, a little bit, but in the end, they don't care about that flexibility. So they just focus on the first beta, the magnitude. So that's that approach. So this option is available in Affinity as a basis function. You can either use the first one, as SPM does, or you use the first and the second one as a second option, or you can use all the 3. So all the 3 options are available in Affinity. So that's the same description. So multicollinearity, that usually you would not have this problem, but if you do, there are 2 reasons you may have this problem. The first problem is basically it's a human error. You make a mistake. Suppose 2 conditions, you just use the same stimulus timing file for both conditions. Of course, you end up with multicollinearity, right? So you end up with 2 regressors exactly the same. So that's one possibility. That's just a booking problem. bookkeeping problem. So the second possibility is that you didn't design your experiment carefully. So, for example, you always have two tasks, one after the other. You follow the same pattern, always A, B, A, B. Those two conditions. Of course, that you may end up with a multicollinearity problem. So those are the two scenarios. But I mean, if you design experiment carefully and be careful about the stimulus timing, you can avoid. But there are tools, definitely you can. Those tools can help you to diagnose the problem. So that's the multicollinearity is a practical issue. Another one is about the residuals. I mean, residuals, it's the last term. Usually people don't care about that. Of course, don't care about them. But in fMRI is because the data is structured. There are temporal temporal structure. So why do we need to care about this? Well, the traditional model for regression is that we have an assumption when we solve it using linear least squares is that the residuals are white noise. It's noise and also white. White it means there's low temporal structure. That means they're totally pure noise. Like the signal processing engineering, and people talk about white noise. There's low temporal structure. There's low, like the two neighboring, the neighboring data points, there's low correlation. Basically, that's the assumption, right? That's why it's called a white noise. When we have problems sleeping, maybe sometimes the white noise will help you, right? But in this case, in fMRI, the data is usually it's not white noise if we simply adopt the traditional regression model, right? Because of the main reason is I think because of the physiological impact, because of breathing, heartbeat. There's that, and also maybe the scanner have some thermal fluctuations that may also contribute to it. But anyway, for this is a very serious problem for block design. When each trial has a long duration, this problem is very severe. The temporal correlation can reach to 0.3. So how to deal with it? So that means the ordinary least squares is not good enough. But what's the impact? Let's first before we talk about the modeling approach. The impact, if you focus on the beta values, you probably will not see much difference whether you are going to take care of the temporal structure in the residuals or not. So the betas, what are the betas? Betas measures the brain response magnitude in the brain, right? So that the property in statistics is called unbiasedness. So that means roughly speaking, the betas are about the same. Roughly speaking, that's called unbiasedness. Of course, in reality, they're definitely not exactly the same, but they're negligible. So we don't need to worry about it. Then you may ask, the impact on the betas are negligible. Why do we need to talk about it, right? So especially when we go to group level, most of the time, people only take beta values, right? But there are a couple of reasons. Sometimes people do care about the individual subgroup analysis result. Why? Because it doesn't have much impact on the beta, but it does have impact on the standard error of the beta values, the reliability information about the beta. So that means the T statistic, the F statistic will be impact, will be changed if whether you take care of the temporal structure or not. What is exactly the impact? It's called inflation. That means the T value would be not much, but higher than the if there's a low temporal structure. So that's why it's called inflated T statistic and F statistic. So that's one reason. People sometimes do care about individual subgroup analysis result. Also, do group analysis. Sometimes people do take both beta and the T statistic to group analysis. Why would the people do that? That's because the betas
the traditional approach, the simple approach, you only take the beta values, you do make an assumption. That assumption, you assume all the betas are equally reliable. People just, do that, make that a strong assumption, and also that approach is much simpler, easier to deal with it. And also, not all software packages have the option of take both beta and t static to group analysis. So for that reason, we do need to take care of the temporal structure. Another reason is that sometimes we want to use the residual to estimate the spatial correlation, the smoothness of the data. So that's another reason we do need to take care of this. So there are multiple reasons. Some of them are for the group analysis, some of them for when we deal with the multiple comparison correction at the group level, when we estimate the smoothness, the spatial extent. So for that reason, we need to take care of it. So for that, in Affinity, we do have an approach. That approach, it's called RMR11, auto-regressive moving average. That approach, we don't want to go to the details, but the idea is to try to estimate to whiten the noise. That's another term to describe it, or to model the structure in the noise. So in Affinity, it's voxel-wise. Each voxel has their own temporal structure. So there's a paper, I think, recently to compare the three software packages. How do they handle this temporal structure, compare their approaches, and compare their impact. So you can read the paper. And roughly speaking, I think Affinity is the most complicated approach because it does voxel-wise. FSL probably in the middle ground. The SPM is the simplest. Probably it's also is the result is probably the worst among the three, I believe, according to this paper. So that's the temporal structure. So another practical issue is that we have multiple runs, usually, right? Usually we only scan the subject for example, 10 minutes, usually longer, right? Half hour, even 1 hour or longer. So multiple runs. The different ways to deal with the multiple runs, as I briefly talked about it before, this is a practical issue. It's not something, about the theoretical things too. So in Affinity, basically we have all the three different ways to do it. That depends on how you want, what you're going to do in the end. So if we don't care about cross-run differences, like habituation effect, or compare whether the same task have different effect cross-runs, if you don't care about that, usually, by default, in Affinity is you glue them together, right? You have multiple runs, you just treat them as just one from beginning to the end. Of course, when specify the data structure, you need to tell the program you do have multiple runs. The practical issue is how do you deal with the multiple runs in the end in terms of the slow drift. That's because each run, we assume they have a different baseline, they have different slow drift. So as long as you tell Affinity you have multiple runs where those discontinuities occur, then the program automatically model the data with different baselines and different slow drifts. So that's in the end, each condition or each task you have just one beta, assuming that you just use the standard curve with 10 multiple basis functions. That's a different story. But anyway, so that's the default approach. That doesn't mean you cannot do the other approaches. Like suppose you do want to compare whether different ones have different effect, whether they have habituation effect. You want to compare the difference across runs. You can do that. You just treat it as in Affinity, it does have the option. You just treat different ones as create a different regressors basically. When you create the stimulus timing files, you have to label them differently. Then that's for Affinity, you just treat it as different tasks. That's pretty much straightforward. So just for those of you who are familiar with either FSL and SPM, I believe in FSL, you cannot concatenate them. You have to treat each one separately. So 3 runs, you have to build 3 separate models, 3 separate models. So in the end, in the neuroimaging field, the term called, that's why I prefer call the individual subanalysis versus group analysis. But some people call it first level analysis versus second level. I believe that's SPM terminology. But in FSL, they call the individual subanalysis as the first level. Then, because of multiple runs, they have to either average those multiple runs. They call that the second level analysis. So the group analysis for FSL would be called the third level analysis. So it's a pretty messy situation. So that's why you really avoid using the first level, second level, or third level. So just straightforward, I just say the individual at group level. So for SPM, you can concatenate those multiple runs, but you have to model them as a separate regressors for each condition. So that's similar to FSL, but it does have the convenience that you can concatenate them, but you have to model them as separate regressors. In the end, probably they do have a way to summarize, to average those multiple betas per condition. So that's this practical issue of dealing with multiple runs. Any questions about this? I mean, it's pretty straightforward. It's just a simple concept. So I think the last issue, practical issue, is the percent single change. I mean, this is more often unique. That's because the 3 software packages, there are 2 different ways to deal with this scanning, normalization of the signal. We know the data from the scanner is very arbitrary, right? So the real values, you see the signal, the numbers are 2,000 or 3,000 or 1,000. It's arbitrary in the sense that you cannot attach any meaning to those numbers because they are different. They can be different. Even baseline can be different from the same scanner across different days, or same subject scanned at a different time point, right? Let alone if you switch a different scanner, even with the same brand. So that arbitrariness is really a headache. So that's why usually we have to standardize it to calibrate the signal. That calibration is called in Affinity we call it scanning. How to standardize, how to calibrate, that's the subtlety here. In Affinity, we do it at each voxel separately. So how do we do it? So we have suppose we have 200 time points. We divide by those 200 numbers by the average of those 200 numbers. Suppose divide then multiply 100. So we do that. Then the idea is, so in the end, you still have the time series, but the values would be roughly around 100 because you divide by the average, then would be roughly around 1, but you multiply 100, so it would be 100. So in a model, remember the baseline, Affinity is just the intercept. Then the regressors are something above that intercept. So we assume because we divide by the average, then we have the baseline is roughly about the average. So the real regressor of interest would be something above that. So that would be, we can interpret that as approximation of percentage single change relative to the baseline. So that's why in Affinity, the beta values are interpretable, and we call that percentage single change. So you remember that I said it's approximation. Why it's approximation? Because ideally, we want the beta to be interpreted as the percentage single change relative to the baseline. But nobody knows the real baseline is ahead of time. Even after we model it, we do get the so-called baseline, but whether that's a baseline or not, we are not so sure. Why? Because there's slow drift. Where do you say there's slow drift? Sometimes it goes up, sometimes it goes down, or sometimes you have both situations, right? So it goes up, but then goes down later on. Where do you say that baseline is? I mean, what's the definition of baseline, right? So we don't have the exact We don't know the exact baseline where it is. So that's why instead of we use the divided by the real baseline because we don't know, we divide by the average of the time series. The 200 numbers, suppose there are 200 numbers, we divide by the average of those 200 numbers. So, but then how good is that approximation, you may ask? Well, I mean, I wrote a commentary about this. I mean, if you do a back of envelope calculation, you will see that approximation is good enough. It's pretty much negligible. It's, I mean, 1% off. I mean, it's percent of the percentage change. So that's the affine approach. It's voxel-wise. So that's why in the end, because it's calibrated, you can compare cross objects. You can compare that beta value across different regions in the brain. So it's interpretable, and it makes sense when you do group analysis.
Doesn't that imply there's some threshold of activity where if you have your block design has a lot of intense stimulus over time, isn't there some threshold where that average is going to get up to a point where it becomes irrelevant?
Yeah, that may have some impact, especially you have, I mean, you have a lot of blocks you don't have enough baseline time period, I guess, but still the impact would be minimal, I think. Nobody has done any, I mean, nowadays that kind of a design is weird. Yes, but it's a legitimate concern, but I don't know my gut feeling is that probably still okay. I have to do another calculation to see how bad that is, if that's really the case. Any other questions? So that's the affine approach. I believe the alternative approach is that they don't do this voxel-wise. Instead, they do for the whole brain share the same calibration. That's called grand mean scanning. So you average across all the time points and also across the voxel, the spatial part. So that's called grand mean scanning. I don't understand the rationale, but that's the way it's done in the field. So in the end, to me, their beta values are a lot interpretable. If they are not interpretable and they are not comparable cross subjects, cross brain regions, then I have trouble understanding. If they are not comparable, then you have trouble understanding why you do lead to group analysis. When you do group analysis, you want to compare the subjects or average them under some common ground, right? If they are not comparable, then what's the point of doing that? So at least conceptually, that's a little bit problematic. So as far as I know, I mean, this also have an impact in the result. When people show the brain image, show clusters, colored blobs, when they show that in affine, as Daniel showed this morning, we have the differentiation between the beta and the t statistic. In affine, we specifically ask you to show the betas. We don't want you to show the t. We don't care about the t, except that as long as your t values pass some threshold, the specific t value, whether it's 7.5 versus 3.7, it doesn't matter. As long as it's above some threshold, the p value doesn't mean much. For us, the beta is the most important thing because the beta shows the real magnitude. The t value, maybe it's some indirect indication of the brain response, but t is dimensionless because it's divided by the same scale, right? So it doesn't have interpretation. For many reasons. I mean, we wrote a commentary about this issue 2 years ago about this. It's because, first of all, maybe this is dramatic, but usually I use in physics, if you want to suppose we measure the distance between Earth and the Moon, in the end, you don't tell me the distance. You just say my t value is such and such. Is that something physicists would agree? I mean, would happy to say? Of course not. But the strange thing is in brain imaging, people don't talk about the brain wave response. They just show you the t statistic, show the p value, the magic number 0.05. Well, I mean, that's the unfortunately a reality in the field for over a quarter of a century. That's how it has been going on. Right? So that's just for this. And when you compare different studies, you do want to compare the whale magnitude. You don't want to compare the t-statistic. Also, when you do meta-analysis, that's pretty popular nowadays, right? You want to summarize across different studies. I mean, nowadays the meta-analysis is just so crude. They don't use betas. They don't even use the t-values either. They just find the so-called peak voxel, then draw a sphere, then make an assumption, then do a meta-analysis across different studies. They don't care about the beta values. That's because in the field, multiple reasons. One, the major reason is people don't report the real effect estimates, right? So that's what's going on. So that, I mean, I can keep babbling about this for a long time, but the point is here, and it's a good habit, and it's a healthy way to move forward in the field. We do want to report. So not just for the whole brain image, and also report the RI level result. We also want you to report the whale beta value, the whale effect estimate. I believe in other software packages, there is a probably work around the solution. For example, I heard there's a package called the Mars bar, right? It's a MATLAB package. You can use that to convert the beta values from your group analysis to percent single change. If you really care about that, why do you the first step just do it during the pre-processing? Then you don't need to that is so-called Mars bar to do that conversion, right? Why do you need to go through that steps? I think one defense I heard in the FSL camp, they argue that if they do voxel-wise scanning, they may have trouble around the edge, the border of the brain. They have some irregularities, but I don't understand what what kind of irregularities they're talking about. But anyway, so at least I haven't seen such a problem yet in FNE. Maybe there is, but they're at the border of the brain, the mask. I mean, that's easy to take care of. We don't really trust those voxels are on the border. I mean, why do we need to sacrifice those? I mean, just because of those few voxels, we sacrifice the interpretability of the beta values, right? So that's my argument, my defense of the approach. So I think this is probably pretty much my last slide. I mean, when we look back, when we do FMI, the individual level, I mean, nowadays it's just routine, but usually we don't do a good job in model. That's because we can only explain a small portion of the signal, I mean, in the data. That's because we don't fully understand the mechanism of the both signal. We just use whatever available in whatever implementation. In the end, we have to be content what do we have. So that's the individual level. At the group level, it's pretty much similar. Which I will elaborate probably on Wednesday. It's a similar situation, the modeling approach. But we have to go this baby steps. I mean, to build on from previous results, try to improve the modeling. So this is basically, this talk is focused on the individual level with the typical routine. As the last slide I summarized here, it's also I showed at the beginning as a preview. So it's in summary, basically we have three different ways to model. One is just use the standard curve, right? So there's just the empirical curve, right? So that's the simplest approach. In the end, when we have one beta per condition. Second approach, we don't make any strong assumption about the shape. Instead, we try to pull out the shape information from the data. We trust the data, right? So that's in FNE we call either use the tents, multiple tents, or use the cubic spline. The difference between the two is pretty negligible. Also, I want to emphasize that in FNE, that's another subtle difference between FNE and other implementations, that if you use there's multiple basis functions, your stimulus timing does not have to be synchronized with your TR. Can be anything. I mean, TR is when the scanner of the to acquire each volume, right? The beginning of that each acquisition. So the TR grid, the stimulus timing, the task, whatever the events or trials, they don't have to be start exact at the beginning of the TR. Can be anywhere. That's even if we use this approach. But I believe in other implementations, they do require the stimulus timing to be locked with the TR. If they are not locked, I don't know whether they have a solution or not. But at least in their implementations, that's a requirement. So that's some subtlety about that multiple basis function approach. So the middle ground, that's a SPM approach. It's also available in F-NITs. You have three basis functions, right? So you have this canonical curve, then there are two adjustments. One modulates the where the peak location. The third one adjusts the width of the peak. So that's then we talk about the few practical issues such as concatenation and the percent signal change. All right, I think I finished 5 seconds ahead of time.